Hello everybody, this is day 2 of L'Hopital's rule, section 8.2. We have more than one indeterminate form. The one we talked about previously was 0 over 0. In this case, we could have infinity over infinity, infinity times 0, and even infinity minus infinity. In the book it says a version of L'Hopital's rule also applies to quotients that lead to the indeterminate form infinity over infinity. If f of x and g of x both approach infinity as x approaches a, then, well, it says we can take the derivative of the top and the bottom in an effort to find the limit, provided the latter limit exists. The a here, and in the indeterminate form 0 over 0, may itself be finite or infinite, and may be an endpoint of the interval I of theorem 5. Example 4, working with indeterminate form infinity over infinity. Identify the indeterminate form and evaluate the limit using L'Hopital's rule. Support your answer graphically. Now, we're looking at secant, and if we, if we graph secant, secant is the reciprocal of cosine. So here's a quick version of cosine. Anywhere cosine is 0, secant is going to be undefined, so we have an asymptote there. And then here is pi over 2, and this would be 3 pi over 2. Now we invert cosine between the asymptotes, and there's your secant function. And as x approaches pi over 2, secant is approaching infinity. And if we look at, so this is going to be infinity, over, if we look at tangent, tangent at 0 is 0, and then once we get to pi over 2, we have an asymptote, and this is what tangent looks like just on the right side of 0, because we're approaching pi over 2, so it is also infinity. So we have infinity over infinity, and so I have identified the indeterminate form we have. It is infinity over infinity, as the title of example 4 suggests. So now we're going to take the derivative. Limit as x approaches pi over 2, this is L'Hopital's rule now, is secant of x tangent of x over, well, the derivative of 1 is 0, and the derivative of tangent is secant squared. Now we're going to do a little bit of trig here to simplify this. First of all, one of the secants is going to cancel, leaving tangent over secant. And then we can do a little bit more with this. As x approaches pi over 2. Tangent is sine over cosine, and secant is 1 over cosine. So we have a complex fraction. If we multiply the top and bottom by cosine, it reduces to just sine. So we have the limit as x approaches pi over 2 of simply sine of x. And now we can actually plug pi over 2 in. Sine of pi over 2 is 1. The answer is 1. In example 5, we are working with the indeterminate form infinity over infinity once again. It says identify the indeterminate form and evaluate the limit using L'Hopital's rule. Support your answer graphically. Well, the natural log of x, if we look at that graph, it does pass through the point 1, 0, and it does go off to infinity. And the square root of x, I know it says 2 times square root of x, but really we're looking at square root of x. It starts at 0, 0, and it does eventually go up to infinity. They look somewhat similar, but the important part is the indeterminate form is infinity over infinity. So we're going to use L'Hopital's rule to try to find the limit of the function altogether. Derivative of natural log of x is 1 over x, and the derivative of 2 square root of x is 2 times, well, I'll just write it like this. 2 times 1/2 square root of x, and square root of x now is on the bottom, so the 2 and the 1/2 cancel each other out. So we have limit as x approaches infinity of 1 over x over 1 over the square root of x. To simplify this, we can multiply the top and bottom by x, which is the limit as x approaches infinity. X over x is going to be 1, and then x over x to the 1/2 would be like taking x to the first power divided by x to the 1/2 power. Let me write that out. We have x to the first over x to the 1/2, and I'm talking about right there, that little piece of the puzzle. When we divide of variables with powers, we subtract the powers. 1 minus 1/2 is 1/2, so we have the square root of x in the denominator. Now if we plug infinity into the square root, the square root of infinity is still infinity, and 1 over infinity is 0. In example 6, it says we are working with the indeterminate form infinity times 0. So if you plug infinity into x, you get infinity, of course. And if you plug infinity into x for the second one, you get the sign of 0, and the sign of 0 is 0. So this indeed is infinity times 0. Now that's one of the indeterminate forms, and we might be able to solve this with L'Hopital's rule. So let's give it a shot here. We have the limit as x approaches infinity, and in this case I want to create a fraction, and we can create a fraction by writing this as the sine of 1 over x over 1 over x. Now imagine what would happen if we multiplied the top and bottom by x here. It would go right back to where we began. So I've changed what it looks like, but the value has not changed at all. Now using L'Hopital's rule, we have the limit as x approaches infinity. The derivative of sine is cosine, so we have cosine of 1 over x, and the derivative of 1 over x, remember you have to do chain rule, derivative of 1 over x is negative 1 over x squared. And to find that out, you can just write 1 over x as x to the negative 1. Take the derivative, you get negative x to the negative 2, and there you have negative 1 over x squared. Now on the bottom, we're going to take the derivative of 1 over x again, and we get negative 1 over x squared. Now the negative 1 over x squared is going to cancel out, so we have the limit as x approaches infinity of the cosine of 1 over x. Now we plug infinity in for x, we get cosine of 1 over infinity. 1 divided by infinity is 0. We have the cosine of 0, which is 1. And there's your answer. Working with the indeterminate form infinity minus infinity. Well, let's look at this. If we plug 1 into the natural log of x, we'd have the natural log of 1 minus 1 over 1 minus 1. That's 1 over 0 minus 1 over 0. And 1 divided by 0 is actually, if we're doing limits, as we approach 1, you get infinity minus infinity. Now that's one of the indeterminate forms that L'Hopital's rule might be able to solve. So we need to write this as a fraction. And to do that, I know they're two separate fractions, but we want to get them to be one fraction so we can take the derivative of the top and the bottom. We're going to do that by writing common denominator. So I'm going to multiply this one by x minus 1 and the right one by the natural log of x. On the top and bottom, of course. So we have x minus 1 minus the natural log of x. That comes from the top, of course. And then we'll put that over the common denominator, natural log of x times x minus 1. Now we can take the derivative. That's what L'Hopital rule says to do. We have the limit as x approaches infinity. Derivative of x is 1. The derivative of minus 1 will be 0, and the derivative of natural log of x is 1 over x. Over. On the bottom we have a product, so we're going to have to use the product rule. First times the derivative of second, which is just 1, plus the second times the derivative of the first, which is 1 over x. Now if we multiply everything by x, I can get rid of the complex fractions. We have equals the limit as x approaches infinity of x minus 1 over x natural log of x plus x minus 1. If we plug infinity into this now, we're not plugging infinity in. Let me go back. I'm just used to writing that now that we're in this section. We're not doing this to infinity. We're doing this as x approaches 1. Excuse me, I'm sure you're quite confused as to why the 1 switched to infinity, but it should not have. So rather than redoing this all, I think I'll just keep plugging ahead. So if we plug 1 into the top, we would get 0. If we plugged 1 in the bottom, we'd have 1 times 0 plus 1 minus 1, and we'd get 0 over 0. Now that's another indeterminate form, so we can keep using L'Hopital's rule to attempt to find this limit. So we have the limit as x approaches 1 of, well, the derivative of the top is just 1, over, and here we have the product rule again, first times derivative of second plus second times derivative of the first, and the derivative of first in this case is just 1. Derivative of x is 1, and the derivative of minus 1 would be 0. Now the two x's are going to cancel each other out here, creating 1 plus 1 is 2. So we have the limit as x approaches 1 of 1 over 2 plus the natural log of x. And if we plug 1 in for the x now, we get 2 plus natural log of 1, and the natural log of 1 is 0, so our final answer is 1/2. And in this case, we had to take the derivative 2 times to get to our answer. There are other indeterminate forms that L'Hopital's rule might be able to handle. They are 1 to the infinity, 0 to 0, and infinity raised to the 0 power. That says limits that lead to the indeterminate forms 1 to infinity, 0 to 0, and infinity to 0 can sometimes be handled by taking logarithms first. We use L'Hopital's rule to find the limit of the logarithm and then exponentiate to reveal the original function's behavior. Now it says the limit as x approaches a of the natural log of f of x equals some limit. Now that goes to the limit as x approaches a of f of x is equal to e to the natural log of f of x, which will be e to the limit. Now I'll explain that by just working an example and showing you how we proceed from there. It says in section 1.3 we use graphs and tables. Well, we didn't do section 1.3, so that's a moot point. Example 8, working with indeterminate form 1 to infinity. Well, if you plug infinity into x here, that would be 1 over infinity, which would be 0. 1 plus 0 is 1, so we have 1 to the power infinity. That's an indeterminate form. Now what we're going to do is we're going to let f of x equal the 1 plus 1 over x raised to the x power. What we can do from here is take the natural log of both sides. So we have natural log of 1 plus 1 over x to the x. And what that allows us to do is to get this x out of the exponent. So now we have x natural log of 1 plus 1 over x. Well, in order to apply L'Hopital's rule, we're going to need a fraction here. So we have natural log of 1 plus 1 over x divided by 1 over x. Now remember, we're trying to find the limit as x approaches infinity of the natural log of 1 plus 1 over x over 1 over x. Now we can take the derivative of the top and the bottom. I almost said both sides. So we have the limit as x approaches infinity of 1 over 1 plus 1 over x times the derivative of 1 over x is negative 1 over x squared. And of course the denominator is also 1 over x. So when we take the derivative of that, we get negative 1 over x squared, which these two are going to cancel each other out, just like we saw in an example earlier. I can see I have example 9 in the way. Let me move that down. There we go. Create a little bit of room here. Oh, what do we have? We have the limit as x approaches infinity of 1 over 1 plus 1 over x. Now, if you plug infinity into x in this case, we have 1 over 1 plus 0, which the answer is 1. But that's not the answer to the original function. That's the answer to the natural log of the function. So then we write, well, the natural log of f of x, that is the limit as x approaches infinity, is equal to 1. Now, it's the natural log of f of x that equals 1, not the limit itself. So now what we can write is the limit as x approaches infinity of e to the natural log of f of x equals e to the first. Now you're thinking, well, how can we just write that? How can that even possible? Take the little equation x equals 4. Now if you wrote e to the x equals e to the fourth, in order for e to the x, in order for e to the x equal to e to the fourth, x is going to have to be 4. So you really haven't changed the value of what x is, you've just changed the way the equation looks. Now, when you have e raised to the natural log, those two things cancel each other out, and we have f of x equals e to the first is just simply e. The answer is e. Let's look at a very similar type of problem. In example 9, well, let me make this a little bigger so you can read a little better. And this is in your book, of course. In example 9, working with indeterminate forms 0 raised to the 0 power, we're going to do the exact same process. We're going to let f of x equal x raised to the x. We're going to take the natural log of both sides. And that's going to bring that exponent down in front. So we have x natural log of x. We need a fraction. So we have natural log of x over 1 over x. Now we're going to use L'Hopital's rule. So I'm going to reintroduce the limit. So x approaches 0 from the right of the derivative of natural log of x is 1 over x. And the derivative of 1 over x is negative 1 over x squared. And of course, we're going to multiply the top and bottom by x squared, which is equal to, it's going to still be negative. Let me write limit, erase that. Limit, as x approaches 0 from the right, of x over, well, it's just going to be 1, so it's just negative x. Let me fix that up a little bit again. Limit, as x approaches 0 from the right, these are going to cancel out, making negative 1, and the top cancels out to make x. So the limit in this case is equal to 0. But that, of course, is not the answer to the limit of f of x. It's the answer to the limit of the natural log of x. So we have the limit as x approaches infinity. No, not infinity. Boy, I really want to write infinity, don't I? Not infinity, but 0 rather. X approaches 0 from the right. We found the limit of the natural log of f of x equal to 0. Well, in order to get rid of that natural log of x, we'll write e to the natural log of f of x and e to the 0. Well, these are going to cancel each other out, so the limit as x approaches 0 from the right of the original function that we wanted is equal to 1. E to the 0 is 1. In example 10, we have working with indeterminate form infinity raised to the 0 power. So we have infinity raised to the 0 on this limit. We're going to let f of x equal x to the 1 over x. Again, just like we did before. We're going to take the natural log of both sides. And that's 1 over x natural log of x. And this can be written as natural log of x over x. Now we're going to use L'Hopital's rule. And we're approaching infinity this time. The derivative of natural log of x is 1 over x. And the derivative of x is simply just 1. So we have the limit as x approaches infinity of simply 1 over x, which is 1 over infinity, which again is 0. Well, that is the limit of the natural log, not the limit of the function itself. So in order to find the limit as x approaches infinity, we're going to have e to the natural log of f of x equal to e to the 0. Natural log and e are going to cancel out. We have the limit as x approaches infinity of f of x is equal to 1, again, for example, 10.